Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're going to talk about power sources for space. Everybody wants to go to space, but you do need power to do things in space. So let's dive deep into it. So first, the daddy is the solar. Now it's the core power supply. This is how we imagined it and this is how we are doing it. So this is one of the core things of it. And it allows us to do tasks, projects and stations. Everything runs on solar. It's the backbone of everything. Now, our local space, what does local space mean? Low Earth orbit, base geostationary orbit, till Mars. Basically, once you start to touch gas giant, is like, yeah, you are not in local area, so to say. But inside that local area, basically Mercury, Venus, Earth, Mars, you do not actually have to worry about energy. There is enough flux, solar flux, that your solar panels can work. Now, can it work in Jupiter, Saturn, Uranus, Neptune, Pluto? Yes, but it would be way too weak. Meaning it starts to reach a point where you have to engineer everything around that power constraint. So there is a penalty to that. Again, like from our luxurious Earth's vantage point, even Mars feels weak. So there is that. But again, practically speaking, you do not have to worry about too much as long as you are in this era, so to in this distance, basically 12 to 15 minutes from sun, you good, you got this. And the biggest benefit is there is no weather obstruction. For example, solar would have solved whole planet's energy issue if there was no weather. For example, sunlight comes up, the solar panel works, the end, our problem would be solved. But that's not how it is. You have fog, you have snow, you have rain, you have clouds. All these things are basically, you hope that sun is out and weather is clear and you get it. But in space, it is that sun equals power. The end. There is nothing, no obstruction. So that's a very good thing. That also means your satellites are reliable, your space stations are reliable. Their power source are like something you can count on. That's the good part of it. There is no that. And you have to understand there is certain side effects. Is like all orbits have some shadow time. Now some have bad shadow timing, meaning up to 50% of the time they will be in the shadow. Some have very good, whereas like 80% of the time it's not in shadow. So depending how your orbit is, how it's arranged, you can get very good uptime or 50% downtime, so to say. So you have to be very mindful. And if you want 24/7 power or 24/7 work, you do have to use batteries for it. That's why all satellites from day one were really corely focused on batteries also, because without battery, even though solar is there, you're not gonna do much. So that's there. And for example, geostationary environment is really good, because again, majority of the time you are in the sun, but there is a small eclipse when you cross the shadow of Earth. At that time you do not get power. But again, some people are saying it's almost like 1 hour of shadow time and 23 hours of solar time. And there is a benefit of that. If that's the alignment you have chosen, is that your solar panel would be huge, your battery would be relatively small, because it only has to jump over 1 hour. But if you're talking about ISS has to have a huge battery. Why? It's sun, basically shadow time is almost 50%. Meaning it's like 20 minutes in the sun, 20 minutes in the shadow, 20 minutes in the sun, 20 minutes in the shadow. And you're like, oh damn. That means almost 12 hours is in the sunlight, charging, 12 times discharging. So you have to be very mindful of these things also, especially like orbit. That's why sun synchronous orbit are so desirable. It's always in the sun. So that's aside. Let's say you sorted it out, you scaled your battery accordingly. The biggest problem is the harsh environment of space. Now we put solar panels on outside and we see things having to it. For example, rain drops, hailstorm, snow, ice, dirt, these sort of things happening. So we can easily see why it's degrading. Now you're like, okay, nothing is there, it's vacuum, so that means it's GG. Not really. The worst thing that happens to it is temperature swing. For example, especially like ISS, like we have the solar panel, sun goes on the solar panel, we get energy, everybody has. Here's the deal, it also heats up. And because there is no environment around it, there is no gas molecules, it does not equilibrate, it just heats up. So the side that is looking at the sun, it goes ultra hot. How hot? It can go very hot, like ludicrously hot, like almost 150 degrees Celsius kind of hot. And here's the deal, that is not that big of an issue. If you know the upper temperature, that's not an issue, you will engineer for it. It's just that when it goes to the shadow, it starts to cool down. And how badly? Well, thankfully only in the shadows for hours, it does start to lose energy through photons. And because there is no environment, the temperature dump is not that brutal. So your low temperature does not go very low, but again, it still goes below 20. So below 50, depending on design and materials. So you have -50 above 50 or sometimes minus 20, 150. So that happens. That's why panels, albedo, all of those things have to be very carefully designed, managed. Otherwise, the temperature swings, again, depending on your orbit, could wreak havoc. And again, that happened to ISS. ISS solar panels are already gone. So that's why there is new rollout solar panels tested for these and are in deployed right now. They have to replace it. Done, meaning new panels are done. So depending on your temperature swings, your panel will not last very long because it's getting frozen and cooked at the same day, multiple times a day, worst case scenario. Another high radiation environment. While we do not like the atmosphere can add clouds, rain and stuff, while those things are bad, there is something even worse than that for solar panels specifically. It's ultra high energy photons, meaning basically alpha, beta, gamma, all of those things that are coming from the sun is blocked by our atmosphere. This is getting bombarded by it, and especially ultra high energy ultraviolet. Ultraviolet has, like, band, so to say. So high energy, our atmosphere is like, nah, brah. This is like, there is no nah, brah. It's like, yes, brah. It just goes through it. So it decays very quickly. So panel cell technology that will on Earth is like, bro, 25-year warranty. You put it in space, it's like, good luck getting 10 a year out of it. It's bad, basically. So high radiation is also bad. And on top of that, if all of those things are not bad enough, there is a micro missiles going on, which we call micro meteorites. So yeah, that's also there. Although this is like, almost you design your system with enough parallel redundancy that even if one small sector gets poofed, it should still work. So that's the solar part of it. While it does work, it does have certain issues to solve, so to say. Then we come to the most critical aspect, batteries. Now, the first puppy that we launched in space actually had batteries, silver, zinc, primary batteries. Now, what does primary mean? Primary simply means non-rechargeable, meaning it's a chemical engine. You start it, it gives you the power, and then it's done. There is no reversing it. There is no rechargeable, and rechargeable cells are called secondary cells. So silver, zinc batteries, basically these puppies. This is from 1969 kind of photograph. So these batteries were the first thing that got things going, Sputnik kind of going. So that's how things started. And then for heavy duty things like Hubble Space Telescope, International Space, heavy duty puppies, we were using nickel hydrogen batteries, these puppies. Now this is almost like a closed loop gaseous battery, or like almost like a fuel cell. The easiest way to think about it is like a fuel cell, closed loop fuel cell. Now it has certain penalties, but one good thing it has, this puppies last, meaning it can live 15 years or more in real life use case. It's not like, oh, in lab. No. This actually survives that long. And again, ISS just retired their package very recently, and Hubble is still running on these. So that was the most space grade technology. Whereas like I put this into my space station, your space station is more likely to deorbit than this puppy to run out. It's like, this is robust. However, this has been abandoned, so to say. So you have to understand, that's how we started. We had silver, zinc, then we had nickel, hydrogen. However, over time, people realized lithium is supreme. So lithium ion became a thing. For example, there is a company known as Rocket Lab. They have a naughty rocket known as Electron. Now the Electron, they're like, hey, gas generators are expensive. What if you do not make a gas generator? It's like, how do you pump the fuel? Well, what if you have electric motors? Cool, we can make very small BLDC, that's not a problem. How do you power it? Batteries. So they have NMC, nickel, manganese, cobalt batteries to turbo pump it. Now, like, aren't they thermally not safe? Technically, yeah, they are not that safe. Meaning, if you want something to not catch on fire, you will not use that. But again, it's a rocket engine. It only has to work for one shot and few minutes. It's good enough. We are there where it's like, we good enough. Like, we good, bro. We good. And rocket engines catch on fire on their own. So it's like, we good. We good. So in that scenario, we good. Now, how about you use Falcon 9? Basically, this is Falcon 9 battery box. You're like, okay, lithium ion battery, AASY. I'm like, why ASI? It's like asset. Anyway, so that's a lithium ion. So what lithium ion you use here? Again, this puppy has to be reused. It's not like go in space and throw it. So in those scenario, and what will you use in Mars rover? You will use NCA battery, nickel, cobalt, aluminum oxide battery, if I'm not mistaken. Again, that is far more thermally safe. It does suffer in terms of oomph, but it is far more safe. It's like, I got this. Like, you can trust it, kind of safe. So, and again, this is the same chemistry, NCA chemistry is in these puppy. GS Yoxa, a Japanese company that makes cells for, like, one of that cell is almost half kilowatt. So it's a big puppy. It's like 3.7 volt, almost 134 amp power. big puppies. So that was the replacement of this puppy, has been replaced with that. So ISS, a new battery pack and new solar panels. So this is the new battery pack. It's quite surprising. You can find, I can actually find their phone number. It's like, yeah, I'm gonna order like, few $1 million worth of battery. So you can do that if you want to. So that's there. So reality is, as of now, in space technology, we have transitioned to that era of experimenting, where it's like, what if we had zinc, aluminum, and this battery and that battery? All of that is gone. Right now, you have to work very hard to find any new probes, any new station that has anything other than lithium ion. Like lithium ion is just reached the supreme point, where it's like, yeah, again, chemistries are completely open to interpretation. Again, you have NMC, you have NCA, some are using lithium titanate, some are using cheaper options, like especially CubeSats. Many of them are using lithium iron phosphate. So you have a lot of options. There is no discussion about it. But again, overall, people are kind of like, yeah, lithium is more than good enough. It's like, for whatever we need to do, there is a chemistry that is just for that good enough. For example, what if you want something like this, which runs very long lifespan? Okay, lithium titanate LTO cells, those puppy will give you the oomph, it will give you the basically lifespan. The only thing it does not give you is the capacity. So you have to put a lot of it. But again, if you are dealing with, let's say, Starship, that's a viable option. Like, what would be better, having small batteries that you have to swap out every 5-6 years, or like, big puppies that you only have to worry about in 15 years? Again, you will do that calculation in the early days, or you can even have both of them. So basically, for something very critical, you have this battery. Thou shall not touch this battery. For auxiliary loads, or like, non-life critical loads, you're like, okay, we have other batteries, we swap it. And again, if it goes down, that's not an issue. Station does not get threatened. But for CO2 scrubbing, we have this big battery. We do not touch the battery. So that's the whole evolution of battery. We started with fancy chemistries, and now we are like, I shall go with lithium ion. Again, you choose what lithium, but that's it. Then we come to the hot puppy, basically radioisotope heater units. I like, wait, heater units? Yeah, because space gets cold. Now, cold is directly proportional to the time. For example, when a space station goes to the shadow, it starts to cool down. The moment sun becomes away, you start to dump photon. Basically, your photon is unbalanced. Input photon is no longer there, output photon is still there. So you are starting to cool down. But you're not going to be in the shadow for very long duration. So you do not drop too much temperature, because again, vacuum is the perfect insulator, and photon output is not really that high. So you do not get that cold. However, let's assume you are on moon and you are going through the night side. 15 days is long time for photons to dump energy. And there is this one side effect, that photons keeps working until you reach absolute zero. So you can get cold, like so cold that majority of chemistry based equipments will stop functioning, meaning batteries will no longer work. Meaning it's just like, yeah, it's dead, it's cooked, it's frozen, basically. Yeah, it's done. So, and again, even electronic circuits could have a hard time. Sometimes you could literally have your PCBs cracking and lead solder balls cracking, because again, the temperature went too low. So that creates a very serious scenario, and that's just 15 days. And what if you go into deeper regions, basically Jupiter, Saturn, Uranus, Neptune, Pluto? You go that far, there is not enough solar flux. So at that point in time, hibernation becomes basically end of mission. And again, you must have seen recent interest in lunar surface. Majority of the, yeah, just 15 days. Get the work done in 15 days, and other than that, bye-bye. You may turn on, but it's like bye-bye at that point in time. So people came up with the idea, it's like, hey, we have radiation. Why not we convert radiation into heat and just forget about it? So that's the whole point, because you have electricity. Whatever mission you are doing, you most likely have electrical sources, whatever it may be. So you can waste energy just to keep yourself warm, or save that precious energy to do something useful. So the idea is, you do no longer need to spend weight and power in order to keep yourself hot. So we are making Cassini. This puppy is going far deep into gas giants. So like, yeah, its sun is not able to keep it warm, and it will get cold. Like, it will just keep getting colder. It's like, okay, how do we design to solve it? Well, old school would be like, hey, just put batteries into it, and bigger solar panels, or whatever, RTG, bigger RTG, and more energy just goes into battery, then goes to heaters to keep everything right temperature. Or we do hot puppy, this puppy, basically radioisotopic plutonium-238. So we find a very small amount of it, for example 2.65 grams of it, and it's a plutonium oxide. The idea is, plutonium oxide is almost like a ceramic, so it does not turn to dust, meaning your rocket is going, it goes kaboom, so it will not scatter like a dust. It will fall like a big chunks, and most likely one intact chunk should be fallen. And again, in this scenario, it will be intact, trust me. It is like small thing encased in metal thing, encased in other graphite thing, with other epoxy thing, with other shielding thing, then it's like a surprisingly well shielded thing. So likelihood of a rocket able to damage this is very low, and it's very small. So it's most likely yeet out of there. So this puppy is only 1 watt of heat. Now 1 watt may sound very little, but yes, but here's the space is not cool. There is no atmosphere that is leaching energy away from you. It's just photon flux. So if you calculate it right, so it's like, hey, how many photon flux, what is the photon dump output of it? So if it's not doing anything, it's idling. It's like, hey, I'm going there, there is nothing, I'm idling. I need minimum 100 watts of basically energy in order to maintain the outflux. I'm dumping 100 watt into space. I need 100 watt input in order to temperature to be stable. You put 100 of these puppy. Some of them have 127 if I'm not mistaken. That's the highest I've seen. So you place it strategically, places that needs that heat, basically battery, basically anything that will be damaged by low temperature, you put there. And you're like, aren't the radiation an issue? No. That's why I said, like, it's only 2.65 gram, and the radiation is only in alpha, majority of them in some amount of beta, and some amount, very little amount of gamma, and ludicrously rare amount of neutrons. So fundamentally, like, from amount to shielding is so good that majority of the energy is converted into infrared, and you just heat it up. So perfect system, and it's never fails. You do not have to worry about, oh, wiring failed or the heater burnt out. Nothing will happen. This is one thing that you're like, you can count on, and you will count on it. Like, once you put it there, never worry about it. So no power, it never fails. First, basically, if you're like, hey, this is not giving energy, that means you have crossed 80 years. So half-life, and again, half-life simply means it will go from 1 watt to half watt. Nothing will happen. It's like, this is not the part that fails. Everything else will fail. This will never fail. And you add as many as you need for warmth. For example, let's say we put some habitats on moon, and you're like, habitats have certain canisters, let's say canisters that are dealing with CO2 system, and you want canisters to be always at 27 degrees Celsius. You do not want that canister to drop below that. Again, you can put 1 or 2 units just around it. So worst case scenario, humans have not touched this habitat in, like, 5 months. It has went through complete darkness. The canisters would be like, me good, me at perfect temperature. So you add as many as you need. We have done this many times. It's not very talked about topic, but it's surprisingly used. Because again, even if you have RTG, why would you want to waste its electrical energy to heat yourself up? And you're like, why can't we conduct the heat away? Yeah, it adds mass. So this few gram object versus hundreds of gram of heat pipe, people are like, yeah. So this is a very cool technology. Then we come to the actual powerhouse that allows us deep space exploration. Radioisotope thermoelectric generator. Now this puppy is when you need 24/7 power, and you do not give a damn from distance from sun or whether sun is out or not. So basically, if you're on Mars and it's nighttime, you don't give a damn. It's like, I do not care. There is dust storm. I don't give a damn. I am in Jupiter. I don't give a damn. I am on Pluto. I don't give a damn. So that's the point when you use these puppies. Plutonium-238 dioxide, and this again, same puppy. As you can see, these is primary and alpha emitter, meaning the lowest form of radiation. Alpha, beta, gamma, neutron. So alpha is like, who cares? Beta is like, put some aluminum foil. Gamma is like, yeah, worry about it. Neutron, run away. If there is a neutron emitter, run. Thou shall not have the technology to stop neutrons. We do not know how to do. Well, other than like put 8 foot of concrete. So that's why this woman can stay so close to this puppy without getting poofed. So that's the benefit of using this exact plutonium-238 dioxide. If a rocket goes kaboom, this will not shatter as a dust. It should shatter in big chunks, which should be easily to clean up, so to say. And again, inside this there are like balls, so it should be continuous. Again, not all designs have that. Voyagers had ball designs, other had different designs to make sure that in case rocket going kaboom, it should not turn to dust. It should be very easy to recover, clean up, so to say. So alpha emitters. Now let that be very clear. Alpha emitter is the primary source. You will have little bit of beta, little bit of gamma, very little amount of neutron, but again, you will put shielding exponentially more than that. Like if you need shielding of like, let's say 1 millimeter, you put 2.5 millimeter of shielding to be damn sure. So and be mindful, when you are in deep space, there is already high energy radiation there. So it's like, yeah, radiation of this is not that big of a deal. So, and half-life is 80 years plus, meaning everything else will decay before this puppy does. So you do not have to worry about it. And again, it has happened with Voyager, where it's like Voyager was like hundreds of watt, baby, lot of power, good power, and then it started to degrade. Now again, RTG did not degrade. The piezoelectric elements, the thermoelectric, thermoelectric elements, they started to degrade. It's basically like how solar panels degrade. Those are the same thing. That's the same ceramics, same technology, so to say. And again, over time, you are exposing it to constant alpha radiation. It's like, yeah, it's like, water slowly chipping away at a mountain and grinding it away. Same thing happens there. And again, those little photons of gamma radiation, while one or two will not do a damage, do enough of it for 20 years, 30 years, 40 years, yeah, this puppy will go from 400 watt to 40 watt. So that does happen. But again, for 5 to 10 years, you do not even have to think about it. We have data, real world test data from Cassini, Voyager, Apollo, and Mars rovers, that you do not have to worry about it. You good. You do not have to worry about it. Hundreds of watt for decades. That's the good part. And when you need to do some heavy puppy, for example, this, and it has a drill to go drrr, and again, drill will take far more than hundreds of watt that it has. So you trickle charge batteries, and battery, when it's fully charged, is like, okay, now I'm ready for drrr operation. So this is how we do radioisotope thermoelectric generator. Like, this is the backbone of deep space. Now let's come to the dream that everybody has, like lunar colony. And I mean colony, not just like going tappa, coming back. Not that. Going there, establishing a human colony. Now for that you need power. And again, I'm adding Mars just for lol sake, but you need even large amount of power for Mars. So we need a lot of energy, like lot. So basically it's a scenario where you need everything plus the kitchen sink with some extra things. You need everything. So RTG will be used. Now, like, why won't we use solar? No, you still would use RTG. RTG will be used for life critical stuff, meaning things that cannot go oops. They cannot have the power supply compromise. They will have RTG, and RTG has secondary benefit, especially for habitats. If it is exposed to lunar winter, lunar night, so to say, the heat load, the fact that RTGs dump enough waste heat that you can maintain it at stable temperature. Even if you like design the thing to handle very low temperature, you don't want it to cycle. Like how long your habitat will last is directly proportional to the temperature frustration it is dealing with. So if you're like cover it properly with a regolith and temperature is fixed, like it shall not go below 27 degree, it shall not go above 32 degrees Celsius, it's gonna last for decades, maybe even century. But the moment you're like, okay, in sunlight it goes to 150 degrees Celsius, again you will have insulation and cooling inside, but in winter, winter as in night, it goes down to like minus 50 degrees, yeah, it's gonna fatigue. Again, ISS is fatiguing for that exact reason. It's not oxygen, it's not corrosion, it's fatiguing. You're like, you don't want that. So that's why that thermal load, that can fix, basically flatline the temperature of the habitat. That's a very good thing, very long lasting thing. That's why RTG will always be used for critical things like life support and bare minimum walkie-talkie kind of communication. And again, we can communicate in very low power to Earth, like 4 or 5 watts is needed. We good. I'm pretty sure even the Apollo, the RTG they have left, maybe still have more than enough power, and we should collect it. We should put all of them in bonfire position where it's like, hey, everybody's taking their hand gloves and all that. Yeah, it's the warm pot. We put everything there, put heat pipes from there to the habitats. It's like, hey, this is the heat source. Because again, even if it's completely decayed, it only means it goes from 500 watt to 250 watt. More than enough heat. So that's there. And then we come to the solar panel, like the space giant solar panels. Now those solar panels will be used for heavy communication, basically 4K video talking, lab equipments, computers, rovers. And yes, we're gonna have rovers and they're gonna be rechargeable now. So we're gonna need a lot of power for that. And battery to balance supply and demand, exactly like grid. So that's there. Now you must have heard about NASA's kilowatt reactor. Now can that be used? In principle, yes, but that reactor project has been shut down or put on hibernation, so to say. Although that will allow us to do industrialization, meaning we can actually do things on moon if we have actual reactor, even if you're like, hey, that's only 10 kilo. That's only 10 kilowatt of power, but that's 10 kilowatt constant, like constant. Like you do not, oh, the daytime I have constant power, nighttime. No, you can keep running 10 kilowatt. Let's say, like for example, you have to make bricks on the moon. So what do? You take regolith, you melt it. That's it. You do not do something messy. Just take it, melt it, make sure the volatiles are collected. If it has something useful gas, like let's say oxygen, you collect it. Wasteful gas, you throw it outboard. So you build bricks. You're gonna need hundreds of bricks to like build link pads and like all those things. You're gonna need things for civilization. At that point, reactors are the best way. And again, NASA designed it. But problem is that puppy is a neutron emitter. Meaning when it turns on, it's not the same thing as a Mark rover, like having RTG next to him. You can stand next to a RTG. You're not gonna go poof, but you cannot do that with an active reactor. If reactor is active, it's giving out neutron, you're dead. You did very quickly. So it has to be buried and made sure there is an area that nobody can go in. It's not RTG. RTG is safe puppy in contrast to a reactor. So I could see that people are like, yeah, let's just bite the bullet and put more solar panels, more batteries. And again, some RTGs, of course, I do expect some RTGs or heating elements. But reactor is like pushing it. Early days, I'm easily sure it's pushing it too much. Maybe later, but or maybe on Mars, but right now it's early stage. So we need a lot of combos to actually do things in space. So this was my presentation on power for space mission, so to say. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.